Time, elusive and omnipresent, is a companion we all share, yet it remains one of the most enigmatic elements of our universe. We invite you on a serene journey into the depths of time itself, where science meets philosophy in a gentle exploration of its mysteries. As we embark on this exploration, we kindly ask you to share with us where you are listening from and the time at your location. If you enjoy our content, please consider subscribing to our channel. So let us embark on this quiet journey into time itself, where science and philosophy intertwine, and the mysteries of the universe unfold before us. We hope you find solace in this exploration, and that it inspires you to reflect on the timeless questions that have captivated humanity for generations. In our daily lives, time feels like a constant companion, a backdrop to the unfolding events of our existence. We glance at our watches or phones, marking the hours and minutes as they pass. We schedule our days around these intervals, trusting them to guide us through the rhythm of life. Yet beneath this familiarity lies a profound mystery that has intrigued both scientists and philosophers for centuries. What indeed do we mean by time? At first glance, time seems straightforward. It is the ticking of a clock, the changing of seasons, the inevitable aging we observe in ourselves and others. We speak of time as if it were a tangible entity. We save it, spend it, lose it, and occasionally even find it. But when we pause to consider what time truly is, the complexity emerges. In everyday terms, time is perceived as a sequence of moments, a progression from past through present to future. We experience time as a flow, moving inexorably forward, never halting, never reversing. This linearity is deeply embedded in our consciousness, shaping everything from our language to our sense of identity. It is this intuitive understanding that forms the basis of our temporal experience. However, when we turn to science for a definition, time becomes less straightforward. In the realm of physics, time is often described as a dimension akin to the dimensions of space. It is a parameter that allows us to order events, to say that one thing happens before or after another. This scientific perspective strips away the flow and narrative, presenting time instead as a coordinate on which events are mapped. Defining time scientifically involves considering its role in various physical theories. In classical mechanics, time is treated as absolute, a universal parameter against which all motion is measured. This was the view championed by Sir Isaac Newton, who envisioned time as a constant, unchanging backdrop to the cosmos. Despite its elegance, this model is not without its complications. It assumes time is the same everywhere, for everyone, a notion that later developments in physics would challenge. Then there is the challenge of measuring time. From ancient sundials to modern atomic clocks, humanity has sought to quantify this elusive entity. Our tools have grown increasingly sophisticated, yet they all rely on periodic phenomena, regular, repeating cycles that serve as the metronome of our universe. Whether it is the Earth's rotation or the oscillation of cesium atoms, these cycles provide a means of marking time's passage with ever greater precision. What makes defining time so difficult is that it is not merely a physical concept, but also a psychological one. Our perception of time is subjective, influenced by countless factors, from our mental state to the environment around us. Moments can seem to stretch into eternity or pass in the blink of an eye, depending on our engagement and emotional experience. This subjective nature adds layers of complexity to our understanding, making time both a personal and universal phenomenon. In philosophical terms, time has been a subject of contemplation and debate for millennia. Ancient Greek philosophers like Heraclitus and Parmenides pondered the nature of change and permanence, laying the groundwork for later metaphysical inquiries. Is time something that exists independently of human perception, or is it a construct of the mind, an illusion created by consciousness? These questions continue to inspire philosophical discourse, challenging our assumptions and expanding our perspectives. In modern physics, the notion of time becomes even more intriguing with the introduction of relativity. Albert Einstein's theories reshaped our understanding, demonstrating that time is not absolute, but relative, intertwined with space and affected by gravity and motion. This revelation opened the door to a new way of thinking about time, one where it is flexible, dynamic, and deeply connected to the fabric of the universe. Yet, despite these scientific advancements, time remains an enigma. It is both a fundamental aspect of reality and a construct of our minds, bridging the gap between the tangible and the abstract. As we delve deeper into its mysteries, we find ourselves confronting the limits of our understanding, each answer leading to more questions. In exploring what we mean by time, we embark on a journey that spans disciplines, from the empirical rigor of science to the introspective realms of philosophy. It is a journey that invites us to question not only the nature of time itself, but also our place within it. As we seek to unravel this mystery, we find that time is more than just a measure of duration. It is a window into the profound interconnectedness of existence, a silent companion on the vast and wondrous voyage of life. In the tranquil dance of the cosmos, time reveals itself through the gentle rhythms of the natural world. Here, amidst the quiet revolutions of celestial bodies and the subtle changes of the seasons, time becomes a tangible presence, woven into the very fabric of life on Earth. Before the advent of mechanical clocks and scientific theories, it was these natural cycles that provided the first clues to humanity's understanding of time. Imagine standing on a grassy knoll, watching the sun rise and set, a comforting regularity that has persisted for billions of years. This daily cycle, the simplest and most immediate expression of time, is defined by the Earth's rotation on its axis. Each spin, completed roughly every 24 hours, marks the passage from one day to the next. It is a rhythm so embedded in our existence that it often goes unnoticed, yet it is fundamental to the structure of our lives. The ancients, with their keen observational skills, were among the first to notice these celestial patterns. They observed the sun's journey across the sky, its position varying slightly each day, heralding the changing seasons. The sun's path traced an invisible arc, shifting northward and southward throughout the year, a pattern that gave rise to the concept of the solar year. As early humans watched the sun's behavior, they began to understand its link to the cycles of nature. They noted how the lengthening days of spring brought warmth and renewal, while the shortening days of autumn signaled the time for harvest and preparation for the cold. These observations were not just practical, they imbued the passage of time with a sense of rhythm and continuity. Beyond the sun, the moon also played a crucial role in shaping early conceptions of time. Its phases, from new moon to full and back again, offered a secondary rhythm, distinct yet harmonious with the solar cycle. These lunar cycles, approximately 29.5 days in length, provided a natural basis for the division of time into months. Ancient societies, from the Babylonians to the Chinese, crafted calendars that intertwined the cycles of the sun and moon, revealing a sophisticated understanding of celestial mechanics. The tides, too, whispered secrets of time to those who listened. Governed by the gravitational pull of the moon and, to a lesser extent, the sun, the regular ebb and flow of the sea offered a daily reminder of the invisible forces at play. Coastal communities relied on these patterns for navigation and fishing, their lives intricately tied to the rhythmic dance of the tides. This natural choreography extended to the biological world, where time became enmeshed with life itself. Plants and animals evolved in harmony with these cycles, their behaviors synchronized with the turning of the earth and the waxing and waning of the moon. Birds migrated with the change of seasons, guided by the sun's position in the sky. Flowers opened and closed with the coming of day and night, responding to the subtle cues of light and temperature. In the animal kingdom, various species exhibit fascinating adaptations to these cycles. Consider the Arctic tern, a bird that undertakes an epic migration from the Arctic to the Antarctic and back each year, effectively experiencing 2 summers in a single calendar year. This remarkable journey, driven by the search for abundant food and favorable breeding conditions, is a testament to the profound influence of seasonal cycles on life. Even the human body is a testament to the natural rhythms of time. Our circadian rhythms, those internal clocks that govern our sleep-wake cycles, are finely tuned to the Earth's rotation. These biological rhythms influence everything from our alertness and energy levels to our mood and metabolism. The interplay between light and darkness, mediated by the hormone melatonin, orchestrates this daily symphony within us. Early humans, attuned to these natural rhythms, used them as markers to organize their lives. The construction of ancient monuments like Stonehenge and the pyramids of Giza, aligned with celestial events such as solstices and equinoxes, reveals an intimate connection to the cycles of time. These structures served as calendars, enabling societies to predict seasonal changes and plan agricultural activities. Such observations and constructs allowed early humans to transcend the immediate present, to anticipate the future and reflect on the past. This emerging temporal awareness laid the groundwork for more abstract concepts of time, paving the way for future scientific and philosophical inquiry. In this manner, time in the natural world presents itself not merely as a backdrop to existence, but as a dynamic participant in the narrative of life. It shapes behaviors, influences decisions, and provides a sense of continuity in an ever-changing world. As we explore these natural cycles, we uncover the intricate dance that binds us to the cosmos, a dance that continues to unfold quietly and inexorably with each passing moment. The story of timekeeping begins in the vast, open landscapes where early humans first observed the regular march of shadows across the ground, cast by the unerring path of the sun. It is in these simple observations that the journey of measuring the invisible began. The sundial, one of the earliest devices, harnessed this celestial dance, providing a way to segment the day into more manageable portions. As the sun arched across the sky, a shadow moved with a silent grace, marking the passage of time in a manner that was both elegant and ephemeral. Sundials, while ingenious, were limited by their dependence on sunlight. As human societies evolved, the need for more reliable methods of timekeeping became apparent, particularly in regions where clouds often obscured the sun. This necessity led to the invention of water clocks, or clepsydrae, which provided a more consistent measure of time. These devices, found in ancient Egypt and China, operated by the steady drip of water from one container to another, a gentle reminder of time's passage, akin to the slow trickle of a stream. As we trace the evolution of these timekeepers, we find ourselves in the bustling heart of medieval Europe, where the mechanical clock began to take shape. The invention of the escapement mechanism allowed for the more precise regulation of a clock's speed by controlling the release of its energy in measured intervals. This innovation paved the way for the pendulum clock, introduced by the Dutch scientist Christian Huygens in the 17th century. The pendulum, with its rhythmic swing, brought a newfound accuracy to timekeeping, reducing errors significantly compared to its predecessors. These advancements were not merely technical triumphs, but also reflections of how society's relationship with time was changing. As towns grew into cities and trade expanded across continents, the demand for synchronization in commerce and communication became critical. The clock, once a curiosity, transformed into a vital tool for organizing daily life, and with it, our perception of time shifted from a natural rhythm to a more regimented cadence. However, the pursuit of precision did not end with the pendulum. In the centuries that followed, the relentless quest for accuracy led to the development of the quartz clock. Introduced in the 20th century, these clocks utilized the consistent vibrations of quartz crystals under electrical charge to maintain time with remarkable precision. This was a leap forward, but it was the atomic clock that would redefine our understanding of time measurement. The atomic clock, developed in the mid-20th century, marked a significant milestone in our journey to measure the invisible. By using the vibrations of atoms, specifically cesium, atomic clocks could measure time to within billionths of a second. This level of precision was unprecedented and had profound implications for science and technology. The atomic clock became the standard for timekeeping, defining the second in terms of atomic transitions rather than astronomical observations. These innovations did more than refine our measurement of time. They altered our perception of it. With each advancement, our understanding of time's nature deepened. Time, once a simple cycle of days marked by the sun's movement, became a concept intricately woven into the fabric of reality, influencing everything from global positioning systems to the synchronization of the internet. Yet, even as we strive for ever greater precision, the essence of time remains as elusive as it is fundamental. Our inventions, from sundials to atomic clocks, are attempts to grasp something that is both intimately familiar and profoundly mysterious. They serve as bridges, connecting the ancient rhythms of the natural world with the precise demands of modern life. Each tick and tock a reminder of our enduring quest to understand the invisible. In this pursuit, we find not just the measure of time, but a reflection of our own journey through it. In the serene corridors of thought, where the mind wanders freely across the tapestry of ideas, we encounter the concept of time as Sir Isaac Newton once envisioned it. Here, time is woven as an eternal backdrop, an unyielding stage upon which the cosmic play unfolds. Newton's absolute time, as he termed it, was a singular, steadfast river flowing uniformly, unperturbed by the events that transpire within its current. This vision of time as a constant entity was not merely a philosophical stance, but a cornerstone of classical physics that held sway for centuries. Newton's formulation of time emerged during the late 17th century, a period marked by the dawn of modern science. His magnum opus, Philosophia Naturalis Principia Mathematica, published in 1687, meticulously laid out the laws of motion and universal gravitation. Within these pages, Newton articulated a view of time that was both intuitive and revolutionary. He posited that time exists independently of the material universe, a continuous stream that runs without interruption or variation. Time, in this realm, is absolute, distinguished from the relative perceptions of clocks or the subjective experience of beings. The appeal of Newton's absolute time lay in its simplicity and utility. It provided a universal framework that allowed for the accurate prediction of planetary motions, the ebb and flow of tides, and the mechanics of terrestrial objects. This conception of time as a constant, linear progression enabled the precise calculations that propelled the scientific revolution. It was a model that resonated deeply with the deterministic worldview of the era, where the universe operated like a grand clockwork mechanism, predictable and orderly. In Newtonian physics, time was akin to a vast, unchanging canvas. Events, like brushstrokes, occurred upon this canvas, but did not alter its inherent nature. This perspective allowed for the development of classical mechanics, where equations of motion could be solved with the assumption that time marched forward at a steady pace. The laws of motion, articulated through Newton's second law, femma, presupposed this constancy of time, ensuring that the mathematical descriptions of reality remained coherent across different frames of reference. This absolute view of time was not without its philosophical implications. It suggested a universe that existed independently of our perception, governed by laws that were eternal and immutable. The notion of time as an unchanging backdrop was comforting in its predictability and symmetry, echoing the Enlightenment belief in reason and order. It painted a picture of a cosmos where past, present, and future were distinct, yet seamlessly connected through the unbroken thread of time. For centuries, Newton's absolute time reigned supreme, shaping not only scientific thought, but also the cultural and philosophical landscape. The deterministic nature of classical mechanics supported the idea that, given sufficient information about the present, the future could be predicted with certainty. This view resonated with the human desire for understanding and control over the natural world, imbuing the study of physics with a sense of purpose and direction. Yet, as with all great ideas, the concept of absolute time eventually encountered the limits of its applicability. As the 19th century gave way to the 20th, new discoveries began to challenge the very foundations of Newtonian physics. The advent of electromagnetic theory, the study of thermodynamics, and the peculiarities of light led scientists to question the universality of absolute time. The stage was set for a profound transformation in our understanding of time, one that would eventually culminate in the revolutionary ideas of Einstein. Despite its eventual displacement by more nuanced theories, Newton's absolute time remains a testament to the power of human imagination and inquiry. It serves as a reminder of the capacity of the human mind to construct elegant models of reality, models that, while imperfect, provide a scaffolding upon which future generations can build. In the tranquil space of reflection, we find that even as our understanding of time evolves, the legacy of Newton's ideas continues to shape the way we perceive the universe. As we muse upon the nature of time, we are reminded that each epoch brings its own understanding, its own tapestry woven with the threads of observation and thought. Newton's contribution to this tapestry is a thread of constancy and clarity, a guiding line through the complexities of the cosmos. In the quiet embrace of contemplation, we see that time, whether absolute or relative, remains one of the most profound mysteries of existence, inviting us to explore, to question, and to wonder. In the early 20th century, the world of physics was rife with questions, uncertainties, and possibilities. It was within this fertile ground that Albert Einstein, a young patent clerk in Bern, Switzerland, fashioned a theory that would forever alter our understanding of time. His insights began with a simple yet profound question: what would it be like to ride alongside a beam of light? From this thought experiment emerged the theory of special relativity, a framework that would challenge the very essence of what time meant to us. At the heart of special relativity lies an idea that seems almost counterintuitive. The speed of light is constant for all observers, regardless of their relative motion. This might sound straightforward, but its implications are anything but. To appreciate this, let us imagine two observers, one standing still on a platform and another traveling swiftly on a train. As a beam of light speeds past both, Einstein's theory asserts that each observer will measure the speed of that light beam to be exactly the same. This notion defies our everyday experiences, where speed appears to be additive. Yet in the realm of light and high velocities, the universe plays by different rules. One of the most striking consequences of this constancy is known as time dilation. Time, according to Einstein, does not tick away uniformly for everyone. Instead, it stretches and compresses depending on how fast one is moving relative to another observer. To illustrate, consider an imaginative journey where one twin boards a spaceship and travels at an immense speed through the cosmos, while the other remains on Earth. Upon the traveler's return, they would find their earthbound sibling aged more than themselves. Time, in this sense, flows differently for those who move swiftly, bending and yielding to the fabric of the universe's rules. This thought experiment, known as the twin paradox, elegantly encapsulates the curious nature of time dilation. At first glance, it seems paradoxical that two events, both twins experiencing the same passage of time from their perspectives, could yield such different outcomes. However, it is not a paradox at all, but rather a reflection of relativity's intricate dance. The traveling twins' journey, involving acceleration and deceleration, breaks the symmetry of the situation, allowing differing amounts of time to elapse for each sibling. The twin paradox has been more than just a theoretical curiosity. It has found real-world resonance in experiments involving atomic clocks. These timekeepers, when flown around the world on swift jets, demonstrate measurable differences in elapsed time compared to their stationary counterparts. Such experiments affirm the remarkable prediction of special relativity, showing that time dilation is not merely a product of thought, but an intrinsic feature of our universe. Beyond the twin paradox, Einstein's theory compels us to rethink our very perception of time. In everyday life, we treat time as a constant backdrop against which events unfold, a universal metronome ticking steadily in the background. Yet, special relativity invites us to see time as a dynamic player in the cosmic theater, one that responds and shifts with the motions of its actors. The implications of this are profound, suggesting that our personal experience of time is inextricably linked to our relative motion through the cosmos. Special relativity, while revolutionary, is also a testament to the simplicity and elegance of physics. Einstein did not rely on complex mathematics or esoteric concepts. Instead, he peeled back the layers of assumption, revealing a universe where time and space are woven together in a delicate but flexible tapestry. His insights remind us that the universe often conceals its deepest truths in the plainest of principles. As we reflect on Einstein's contributions, it is important to remember that his theories are not just about the esoteric or the grandiose. They touch upon the intimate and the immediate, influencing technologies that permeate our daily lives. For instance, the Global Positioning System, GPS, relies on a precise understanding of time dilation to function accurately, ensuring that the clocks on satellites, which orbit the Earth at high speeds, remain synchronized with those on the ground. In pondering Einstein's revolution, we are reminded of the beauty inherent in scientific inquiry. It encourages us to question the familiar, to probe the boundaries of our understanding, and to embrace the mysteries that lie beyond. The story of time, as revealed by special relativity, is one of wonder and revelation, inviting us to consider not just how we measure time, but how we perceive and experience it in the ever-flowing stream of existence. Thus, as we continue to explore the nuances of time, we find ourselves not merely observers of the universe, but active participants in its unfolding narrative. In the gentle cadence of time's passage, we are invited to ponder our place within the vast cosmos, to seek understanding amidst the unknown, and to marvel at the exquisite dance of time and space. In the vast tapestry of the cosmos, gravity weaves a most intriguing thread, one that not only holds celestial bodies in their eternal dance, but also bends the very fabric of time itself. This interplay between gravity and time was elegantly unveiled through the profound insights of Albert Einstein, whose theory of general relativity reshaped our understanding of the universe. Imagine, if you will, the universe as a great, pliable sheet. When a massive object, like a planet or star, rests upon this sheet, it creates an indentation, a curvature in the space around it. This curvature is what we perceive as gravity. But intriguingly, it also affects the flow of time. Near massive objects, the passage of time slows down, an effect that is as subtle as it is profound. To grasp this concept, let us turn our gaze to the stars and consider the practical marvel of GPS satellites. These satellites, orbiting high above the Earth, are crucial for navigation, telling us where we are on this vast planet with remarkable precision. Yet, Their accuracy hinges on accounting for the intricate dance of gravity and time. You see, these satellites travel at great speeds and reside in a weaker gravitational field compared to the surface of the Earth. According to general relativity, both these factors influence the passage of time. The clocks aboard these satellites tick ever so slightly faster than those on the ground. Without correcting for these differences, your morning run could lead you astray by several kilometers, and planes would find their courses misleadingly shifted. The adjustment made for this relativistic effect is not merely a theoretical exercise, but a daily necessity, a testament to how Einstein's insights permeate our modern lives, often unnoticed. It is as if we have woven the fabric of the cosmos into the very technology that guides us through our days. But why does gravity affect time? Consider a beam of light traveling through space. Light, in its relentless pursuit of the straightest path, bends as it passes near a massive object, following the curvature of space-time. Time, much like light, is also influenced by this curvature. Near a massive body, the flow of time is stretched, much like the gentle elongation of a river as it winds through a valley. This phenomenon, though imperceptible in our everyday experiences, has been confirmed through meticulous experimentation. Atomic clocks, the epitome of precision, have been placed at differing altitudes, revealing the subtle yet discernible differences in the passage of time. On a mountaintop, where gravity's embrace is slightly weaker, time flows a fraction of a second more swiftly than at sea level. In this dance of gravity and time, we find a universe that is not static but dynamic, where the very fabric of existence is in a state of perpetual transformation. It is a universe where the familiar tick of a clock becomes a symphony of cosmic proportions, resonating with the subtle notes of relativity. As we ponder these ideas, let us reflect on the beauty of a cosmos, where time is not merely a backdrop to existence, but an active participant in the grand narrative of the universe. Gravity, with its gentle yet inexorable pull, shapes not just the orbits of planets, but the very rhythm of time itself. In the quiet moments of contemplation, we find ourselves part of this cosmic symphony, where the notes of gravity and time play on, inviting us to listen with a sense of wonder and humility. Thus, the curvature of the universe becomes not just a scientific concept, but a reminder of the interconnectedness of all things, where the vastness of space and the intimacy of time converge in a dance that has been unfolding for eons and will continue long after our brief sojourn under the stars has ended. In the grand tapestry of the cosmos, the fabric weaves together not just the threads of space, but also those of time. This profound notion that time and space are not separate entities but interwoven into a single continuum known as space-time stands as one of the most elegant revelations of modern physics. It invites us to envision the universe not as a static stage upon which events unfold, but as a dynamic and interconnected whole where the very essence of time and space are intrinsically linked. The concept of space-time arises from Albert Einstein's theory of relativity, which fundamentally transformed our understanding of the universe. In the early 20th century, Einstein proposed that instead of treating time as an independent and absolute entity, as Isaac Newton had done, we should consider it intertwined with the three dimensions of space. This revolutionary idea gives rise to a four-dimensional continuum, where each point is defined by coordinates of both space and time. Picture a vast cosmic quilt, where every stitch represents a location in space and a moment in time, intricately stitched together to form the universe we inhabit. To grasp this concept more intuitively, imagine a loaf of bread. As we slice through it, each slice represents a moment in time, while the loaf as a whole embodies the entirety of space-time. Events unfold within this loaf, not merely as isolated happenings, but as interconnected occurrences that are inseparably bound by the fabric of space-time. This perspective shifts our understanding of movement and events, suggesting that an object's trajectory through space is also its journey through time. In this framework, we can no longer consider motion as simply traversing from one point to another in space. Rather, it's a path through space-time. This path, or world line, describes the history of an object's location in the universe, tracing its journey from the past, through the present, and into the future. These world lines weave through the cosmic fabric, showing us that every movement is a kind of dance through both space and time. When we observe the night sky, we are not merely witnessing stars as they are, but as they once were. Light from distant stars and galaxies travels vast distances across the universe, taking years, centuries, or even millennia to reach us. Hence, we see these celestial objects not in their current state, but as they existed in the past. In this way, space-time offers us a window into history, allowing us to peer back through time at the universe's past moments. The notion of space-time also reshapes our understanding of gravity. In Einstein's vision, gravity is not a force pulling objects toward each other, but a curvature of space-time itself, caused by mass. Imagine space-time as a flexible rubber sheet. When a massive object, like a star or planet, is placed upon it, the sheet bends, creating a depression around the object. This curvature of space-time dictates the paths that other objects take as they move through the universe. Planets orbit stars not because they are being pulled by an invisible force, but because they are following the curved paths laid out by the warped fabric of space-time. This elegant model explains why planets move in elliptical orbits and why light bends around massive objects, a phenomenon known as gravitational lensing. When light from a distant star passes near a massive body, such as a galaxy or black hole, the curvature of space-time bends the light's path, causing the star to appear in a different position than it actually is. This bending of light provides astronomers with a powerful tool to study the universe, revealing the presence of otherwise invisible objects like dark matter. Our everyday experiences are deeply rooted in this interconnected tapestry of space-time, though we might seldom recognize it. Every journey we take, every moment we experience, is part of our world line, weaving through the universe. The flow of time that we perceive is inextricably linked to our movement through space. As we move faster, time itself flows differently for us compared to those at rest, a phenomenon borne out by experiments with high-speed particles and precise measurements of time using atomic clocks. Space-time challenges us to rethink the boundaries of our perception, blurring the lines between what is and what was, between the here and the there. It suggests that the universe is not a collection of isolated moments and locations, but a seamless whole where past, present, and future coexist. This vision of the cosmos encourages us to ponder the deep connections that bind us to the universe, inviting us to explore not just the stars above, but the very nature of existence itself. In contemplating space-time, we find ourselves at a confluence of inquiry and imagination, where science offers us a profound perspective on the nature of reality. It is an invitation to journey beyond the familiar confines of space and time, to embrace a vision of the universe as a unified and intricate tapestry, ever unfolding. In our everyday lives, the passage of time feels like a one-way street, an inexorable journey from past to future, leaving a trail of memories behind us while the future remains an unfolding mystery. This notion of time's unidirectional flow, often referred to as the arrow of time, is something we take for granted. Yet, when we delve into the realms of physics, we find ourselves confronting a curious puzzle. The fundamental laws of physics, particularly those governing the microscopic world, are largely time-symmetric. That is to say, they do not inherently favor one direction of time over another. So, why is it that we experience time as moving forward rather than backward? The answer, as it turns out, lies in the concept of entropy and the second law of thermodynamics. Entropy, in its simplest terms, is a measure of disorder or randomness within a system. Imagine a neatly arranged deck of cards, each suit and number perfectly ordered. This represents a state of low entropy. Now, if we shuffle the deck thoroughly, the order is lost, and the deck becomes a jumbled collection of cards. This is a state of higher entropy. The second law of thermodynamics tells us that in an isolated system, entropy tends to increase over time. In other words, systems naturally evolve from order to disorder. To understand why this is significant for the arrow of time, let's consider a classic example: an egg falling off a kitchen counter. As it hits the floor, the shell cracks, the yolk spills, and the once pristine egg becomes a mess, a vivid illustration of increasing entropy. The process is irreversible. The egg does not spontaneously gather itself back together and leap onto the counter. This irreversibility is a hallmark of the macroscopic world we inhabit. The underlying reason for this unidirectional increase in entropy is statistical. There are far more ways for a system to be disordered than ordered. If we imagine all the possible configurations of atoms in a system, the vast majority correspond to states of higher entropy. Therefore, as a system evolves, it is statistically more likely to move towards these higher entropy states. This statistical tendency for entropy to increase is what gives rise to the temporal asymmetry we observe. It endows the universe with a memory of the past, as lower entropy states are more ordered and thus more easily distinguishable from the myriad higher entropy states that follow. This is why we can recall what happened yesterday, but not what will happen tomorrow. Interestingly, while entropy provides a compelling explanation for the arrow of time, it also raises profound questions about the initial conditions of the universe. For the second law of thermodynamics to hold, the universe must have started in a state of remarkably low entropy. This initial condition is something of a cosmic mystery, as it implies an extraordinary degree of order at the beginning of time. Some theories suggest that this low entropy state is tied to the conditions of the Big Bang, but the ultimate reason remains one of the great unanswered questions in physics. As we ponder the arrow of time, It's worth considering how it shapes not only the physical world, but also our very existence. Our lives are narratives woven from the fabric of time, each moment a page in a story that unfolds in a singular direction. This progression from past to future is what allows us to grow, learn, and experience the richness of life. In the natural world, the arrow of time manifests in myriad ways. Seasons change in a predictable cycle. Seeds sprout and grow into towering trees. Rivers carve their paths through valleys, and mountains slowly erode. Each of these processes is driven by the relentless march towards higher entropy, a testament to the irreversible nature of time's passage. Yet, despite the apparent inevitability of entropy, life itself is a remarkable defiance of disorder. Living organisms maintain and even create order within themselves by consuming energy and expelling entropy into their surroundings. This delicate balance between order and disorder is what allows life to flourish, a fragile dance sustained by the flow of time. In reflecting on the arrow of time, we find ourselves contemplating the delicate interplay between physics and philosophy. While entropy provides a scientific explanation for time's directionality, it also invites us to consider our place within the cosmos. We are, after all, transient observers in a universe where time is both a linear journey and a profound mystery. As we continue to explore the nature of time, we are reminded that our understanding is ever evolving. With each new discovery, we inch closer to unraveling the secrets of time's arrow. Yet, the deeper we delve, the more we appreciate the complexity of this fundamental aspect of existence. In the quiet moments of reflection, we may find solace in the knowledge that, though time marches ever forward, we are part of a timeless dance, a fleeting yet wondrous expression of the universe's ongoing story. In the realm of the quantum, where the rules of classical physics often find themselves wanting, time assumes a peculiar role. Here, we find a world where particles exist in states of possibility until observed, where certainty is elusive and probabilities reign supreme. It is within this delicate dance of probabilities that time in quantum mechanics offers us a different perspective. Quantum mechanics, at its heart, describes the universe through a mathematical framework that predicts probabilities of finding particles in various states. Unlike the certainties of classical physics, quantum mechanics thrives on potentiality. A particle, such as an electron, can exist in multiple states simultaneously until a measurement is made. This is known as superposition, a concept famously illustrated by the thought experiment involving Schrödinger's cat, where a cat in a box is simultaneously alive and dead until observed. In this peculiar quantum domain, time manifests itself in two distinct ways, as a smooth evolution when left unmeasured and as a jarring discontinuity upon observation. This duality is central to the quantum understanding of time. When we speak of the smooth evolution of quantum states, we refer to the Schrödinger equation, which governs how quantum states change over time. In essence, this equation allows for a continuous and deterministic evolution of the state of a system. Imagine a gentle stream flowing, where each particle of water flows predictably, the path of the stream unbroken and smooth. In quantum terms, this is the unobserved state, evolving naturally over time. Yet, the moment we measure a quantum system, the continuity is disrupted. The act of measurement collapses the wave function, forcing the system into one of the possible definite states. This is akin to a sudden, unexpected interruption in our stream, where the water droplets are inexplicably frozen in mid-air, each droplet representing a possible outcome now realized. This phenomenon is known as wave function collapse, and it underscores the discontinuous nature of time when quantum states are observed. This peculiar behavior of quantum mechanics raises fundamental questions about the nature of time itself. In classical physics, time is a backdrop against which events unfold, uniform and constant. However, quantum mechanics suggests that time is intertwined with the act of observation. It begs the question, does time flow independently? Or is it a construct that only gains meaning through our interactions with the universe? The role of measurement in quantum mechanics highlights another perplexing aspect of time: entanglement. In entangled systems, particles can become linked in such a way that the state of one particle is instantaneously connected to the state of another, regardless of the distance separating them. This phenomenon was described by Einstein as spooky action at a distance, and it challenges our conventional understanding of time and space. When an entangled particle is measured, the state of its partner particle is instantaneously determined, as if the information has traveled faster than the speed of light. This instantaneous connection suggests a kind of timelessness, a realm where the separation of space and time dissolves into a single, interconnected entity. The implications are profound, hinting at a deeper, perhaps hidden, layer of reality where time might not play the fundamental role we ascribe to it. In this quantum landscape, the passage of time becomes a subtle interplay between potentiality and actuality. The equations of quantum mechanics, such as the Schrödinger equation, provide a deterministic framework for how systems evolve, yet the outcomes remain probabilistic until observed. It is this juxtaposition of certainty in evolution and uncertainty in outcome that defines the quantum nature of time. As we ponder the implications of time in the quantum realm, we are reminded of the ongoing quest to reconcile the macroscopic world of classical physics with the microscopic realm of quantum mechanics. The challenge lies in bridging the gap between the smooth, continuous flow of time we experience in our everyday lives and the discontinuous, probability-driven nature of time at the quantum level. In this pursuit, physicists continue to explore the boundaries of what we know, seeking a unified framework that seamlessly integrates these two seemingly disparate views of time. Quantum mechanics, with its unique perspective on time, invites us to question our assumptions and to embrace the mysteries that lie at the heart of our universe. Through the lens of quantum mechanics, time emerges not as a solitary stream flowing from past to future, but as a complex tapestry woven from threads of potentiality and measurement, continuity and discontinuity. It challenges us to consider that our perception of time's passage might be but one facet of a richer, more intricate reality waiting to be understood. In this enigmatic dance of particles and possibilities, time remains both a familiar companion and a profound mystery, inviting us to wander further into the depths of the quantum world, where each discovery holds the promise of a new perspective. In our journey through the realms of time, we arrive at a curious crossroad where two giants of modern physics seem to share a polite yet persistent disagreement. These giants are general relativity and quantum mechanics, each providing a framework that has been tested and confirmed to astonishing precision within its own domain. Yet, when it comes to the nature of time, their views diverge in ways that have puzzled and inspired physicists for decades. General relativity, a brainchild of Albert Einstein, paints a grand and elegant picture of the universe. Here, time is woven into the very fabric of space, creating a dynamic stage upon which the cosmic theater unfolds. This stage, known as space-time, bends and curves in response to mass and energy, dictating the paths that objects follow. In this view, time is continuous and universal, a smooth river flowing ever forward. In stark contrast, quantum mechanics, the theory governing the subatomic world, treats time quite differently. At this diminutive scale, the universe behaves less like a serene river and more like a restless sea, with particles appearing and disappearing, governed by probabilities rather than certainties. Time, in this realm, becomes a backdrop against which quantum states evolve. But intriguingly, it does not share the same malleability as in general relativity. Instead, time in quantum mechanics remains fixed and absolute, a silent observer, detached from the quantum dance. This dichotomy presents a profound puzzle. How can two theories, each so successful in its own right, offer such differing perspectives on time? The quest to reconcile this discrepancy has given rise to one of the most ambitious pursuits in physics, the search for a unified theory, often known as quantum gravity. Such a theory would seamlessly merge the principles of general relativity with those of quantum mechanics, offering a coherent description of the universe at all scales. The challenge lies not only in the mathematical complexity, but also in the conceptual leap required. Quantum gravity asks us to envision a framework where space-time itself could be quantized, discretized into the smallest possible units, akin to pixels on a screen. This notion suggests that, at the Planck scale, a realm so minute that it defies direct observation, space-time might exhibit a fundamentally different structure, where the smoothness we perceive gives way to a granular, fluctuating tapestry. Several theoretical approaches have emerged in this quest for unity. String theory, for instance, proposes that the fundamental constituents of the universe are not point-like particles, but rather tiny vibrating strings. These strings, oscillating in multiple dimensions, could potentially reconcile the forces of nature, including gravity, in a harmonious framework. Within string theory, time might emerge as an artifact of a more profound, underlying reality, hinting at a deeper structure yet to be fully understood. Another contender is loop quantum gravity, which seeks to quantize space-time by envisioning it as a network of finite loops. In this model, the continuous flow of time is replaced by discrete transitions, much like frames in a film. This approach suggests that time, rather than being a fundamental entity, could arise from the interactions within this network, a concept that challenges our intuitive notions of temporal continuity. Despite these promising avenues, the unification of general relativity and quantum mechanics remains an elusive goal. Each theory, while internally consistent, resists incorporation into the other's framework, like two pieces of a puzzle that seem to belong to different pictures. The difficulty lies not only in reconciling their mathematical formulations, but also in addressing the philosophical implications that such a unification would entail. Consider, for instance, the notion of causality. In our everyday experience, cause precedes effect, creating a temporal order that underpins our understanding of events. However, in the quantum realm, this order is not always so clear-cut. Quantum entanglement, a phenomenon where particles become correlated in ways that defy classical intuition, suggests that information can be exchanged instantaneously, regardless of the distance separating the particles. This raises intriguing questions about the nature of time and causality, challenging our conventional views. As we ponder these mysteries, it becomes apparent that the problem of time is not merely a technical challenge, but a profound inquiry into the nature of reality itself. It invites us to reconsider our assumptions, to explore the boundaries of knowledge, and to embrace the possibility that time, as we perceive it, might be but one facet of a more intricate tapestry. In this gentle exploration, we find ourselves on the frontier of human understanding, where questions outnumber answers and where each insight opens new vistas of curiosity. The journey to unify the disparate realms of physics is as much about the process as it is about the destination. It is a journey that encourages us to think deeply, to question boldly, and to appreciate the quiet beauty of the universe's most enigmatic dimensions. As we continue to unravel the threads of time, we do so with a sense of wonder, aware that the very act of questioning brings us closer to the truths that lie just beyond the horizon. Here, in the delicate interplay of theory and imagination, we find a reminder that the universe is a tapestry of mysteries, patiently awaiting the touch of an inquisitive mind. In the gentle unfolding of the universe's story, we arrive at a moment that is as enigmatic as it is monumental, the Big Bang. This event, a cornerstone of modern cosmology, is often depicted as the starting gun for time itself. Yet, the question of whether time truly began with the Big Bang is one that continues to puzzle scientists and philosophers alike. To understand why this question is so compelling, we must first consider what the Big Bang represents. Approximately 13.8 billion years ago, the universe as we know it began to expand from an extremely hot and dense state. This expansion, still continuing today, is observed through the redshift of distant galaxies, a phenomenon that marks their recession into the cosmic distance. But was this expansion truly the beginning of time, or merely a chapter in an even grander narrative? The conventional view posits that time and space were indeed born in that initial explosion of energy and matter. Before the Big Bang, the notion of before might not even apply, as time itself may not have existed. However, this perspective raises profound philosophical and scientific questions. If time began with the Big Bang, what caused this event? And if there was a cause, does that imply the existence of a before in some form? Some theories propose that the Big Bang was not the singular inception of everything, but rather a transition between different states of the universe. One such idea is the cyclical universe model, which suggests that the universe undergoes endless cycles of expansion and contraction. In this view, the Big Bang could be likened to a phoenix rising anew from the ashes of a previous cosmic era. Each cycle might wipe the slate clean, with time as we understand it resetting with each new expansion. Another intriguing proposition is the multiverse theory. This concept imagines our universe as just one of many, each with its own distinct laws of physics. In this grander framework, the Big Bang could be a localized event, a bubble forming within a larger cosmic froth. Here, time might be a local feature, relevant only within the confines of our universe, but not a fundamental aspect of the larger multiverse. Quantum mechanics also offers a rich tapestry of ideas regarding the origins of time. The notion of quantum fluctuations suggests that the Big Bang might have arisen from a primeval quantum state, where the familiar rules of cause and effect do not hold sway. In such a state, time might not be a linear sequence but a more complex and interwoven fabric, emerging as the universe cools and expands. The very structure of time itself is questioned by these theories. If time is not strictly linear, then what we perceive as the beginning might be an artifact of our limited perspective. This raises the possibility that time is more akin to a landscape where the notion of a beginning is but a feature of the terrain, not a definitive starting point. The implications of these ideas stretch far beyond theoretical musings. The concept of a universe without a single point of origin invites us to rethink causality and existence itself. If the universe is cyclic or part of a multiverse, then our place within it becomes part of a much larger and more complex story. It challenges us to consider our own beginnings and endings, both as individuals and as a species, within the vastness of cosmic history. Furthermore, the exploration of time's origins intersects with the search for a unified theory of physics. General relativity and quantum mechanics, the two pillars of modern physics, offer differing accounts of time. While relativity treats time as a dimension woven into the fabric of space-time, quantum mechanics describes time in a more fragmented way, where events can occur without a clear temporal sequence. Reconciling these views is one of the great challenges of contemporary science, and the answer may lie in understanding the very nature of time itself. As we contemplate the beginnings of time, we are reminded of the limits of human understanding. Our quest to comprehend the universe's origins is as much about confronting the unknown as it is about uncovering it. The Big Bang serves as a reminder of the mystery at the heart of existence, a mystery that invites us to ponder not only the universe's past, but also its future. In reflecting on these ideas, we find ourselves at a crossroads of science and philosophy. The question of whether time began with the Big Bang encourages us to look beyond the surface of things, to seek deeper patterns and connections. It is a question that touches on the very essence of what it means to inhabit a universe that is both ancient and ever-changing. As we continue our journey through the cosmos, we carry with us the knowledge that time, like the universe itself, is an intricate and boundless tapestry. Whether it began with a bang or stretches back into an eternity we cannot yet fathom, time remains one of the greatest mysteries we have yet to unravel. And in our pursuit of understanding, we find not only the story of the universe, but also our own place within its timeless expanse. In the grand tapestry of the universe, our existence is but a fleeting blink. Yet, the Earth, this delicate blue sphere we call home, unfolds a story of astonishing longevity. A narrative written not in books or scrolls, but etched into the very rocks beneath our feet. Geology, the study of this ancient script, offers us a window into deep time, the vast, almost unfathomable history of our planet. Imagine, if you will, a time when the Earth was young, a swirling mass of molten rock, slowly cooling and solidifying over eons. This process began around 4.5 billion years ago, a span so immense that our minds struggle to comprehend it. We, as humans, naturally think in terms of years, decades, and perhaps centuries. But the timeline of Earth stretches into the billions, a scale that dwarfs our everyday experience. To grasp this concept of deep time, consider a single day. Each second of that day could represent 100,000. In this analogy, the entirety of human civilization would occupy less than a single tick of the clock. It is a humbling perspective, a reminder that our species is but a recent addition to the Earth's long story. The rocks that form the Earth's crust are like pages in a history book, each layer telling a tale of ancient climates and shifting continents. Take, for instance, the Grand Canyon in the United States. Its towering walls reveal around 2 billion years of geologic history. Layer upon layer of sedimentary rock, each one formed in a different environment, a sea, a desert, a swamp. By studying these layers, geologists can reconstruct past landscapes and climates, piecing together the Earth's story. The science of geology not only reveals the Earth's past, but also challenges our perception of time. It requires us to think beyond our immediate human-centric experience. Consider the formation of a mountain range. Over millions of years, tectonic plates collide, fold, and uplift, slowly creating towering peaks. To us, mountains appear timeless and unchanging, yet they are in a constant state of flux, growing, eroding, and reshaping over geological timescales. One of the most striking examples of deep time is the fossil record. Fossils are the preserved remains of once living organisms, offering a glimpse into the history of life on Earth. From the simple, single-celled organisms that first appeared billions of years ago, to the diverse array of plants and animals that inhabit the planet today, fossils provide a chronological record of evolution. The discovery of dinosaur fossils, for instance, captivated the scientific community and the public alike. These ancient creatures roamed the Earth for over 160 million years, a reign that far exceeds the time humans have existed. Yet, their extinction, around 66 million years ago, serves as a poignant reminder of the impermanence of life and the dynamic nature of our planet. But why is it that we, as humans, find it so challenging to grasp these immense timescales? Our brains are wired to perceive time through the lens of our own lifespans. Days, months, and years are familiar intervals, tangible and relatable. In contrast, the concept of millions or billions of years stretches the limits of our comprehension, akin to imagining the vastness of the universe itself. This difficulty is not merely academic. It has profound implications for how we relate to the Earth. It can be all too easy to dismiss environmental changes as inconsequential, believing the planet to be resilient and unchanging. However, geology teaches us that the Earth is both dynamic and vulnerable, its systems intricately balanced and sensitive to disturbance. As we reflect on this vast history, we are reminded of our place in the world, not as masters of the Earth, but as part of its ongoing story. A story that began long before us and will continue long after we are gone. By understanding deep time, we gain a deeper appreciation for the interconnectedness of life and the delicate balance that sustains it. In contemplating the Earth's ancient history, we also glimpse the future. The forces that shaped the planet continue to act today, shaping the landscapes we know and love. As stewards of this world, it is our responsibility to preserve it for future generations, to ensure that our chapter in the Earth's story is one of care and respect. Thus, the study of geology and deep time becomes not just an academic pursuit, but a journey of understanding and humility. It invites us to step back from the immediacy of our daily lives, to see the broader picture, and to marvel at the intricate tapestry of time that envelops us all. In this quiet reflection, we find not only knowledge, but a profound sense of connection to the Earth and its enduring legacy. In the vastness of the cosmos, time unveils itself not as a simple linear thread, but as a grand tapestry, stretching across the universe with complexity and grace. As we peer into the depths of space, the very act of observation becomes a journey through time itself. The light from distant galaxies takes millions, sometimes billions, of years to reach us. Thus, when we look skyward through our telescopes, we are not merely seeing the present moment, but a mosaic of epochs long past, laid out before us in a celestial panorama. This notion of seeing into the past is beautifully captured in the phenomenon known as cosmic expansion. In the early 20th century, astronomer Edwin Hubble observed that distant galaxies are moving away from us, and that their speed is proportional to their distance. This profound discovery suggested that the universe is expanding, a revelation that transformed our understanding of cosmological time. The farther a galaxy is, the faster it recedes, implying that the universe was once much smaller, denser, and incredibly hot. This led to the theory of the Big Bang, the explosive event thought to have marked the beginning of our universe approximately 13.8 billion years ago. The expansion of the universe is not just a curious fact, it is a fundamental feature of the cosmos, allowing us to glimpse time's passage on the grandest of scales. As space itself stretches, the light waves traveling through it are also stretched, shifting towards the red end of the spectrum. This redshift is a cosmic fingerprint of time's relentless march forward, a silent testament to the universe's dynamic nature. In the aftermath of the Big Bang, the universe was a seething hot soup of particles and radiation. As it expanded, it cooled, allowing protons and electrons to combine into hydrogen atoms. This marked a pivotal moment, as the universe became transparent to radiation, permitting light to travel freely for the first time. The remnants of this light, now cooled to just a few degrees above absolute zero, fill the universe as the cosmic microwave background radiation, CMB. This faint glow, omnipresent and ancient, serves as a snapshot of the universe at a mere 380,000 years old, a veritable baby in cosmological terms. The CMB is more than a relic of the past. It is a map of the universe's infancy, peppered with tiny fluctuations in temperature. These fluctuations are the seeds from which galaxies, stars, and planets would eventually grow, under the inexorable pull of gravity. By studying the CMB, scientists have gleaned invaluable insights into the universe's early conditions, its composition, and its subsequent evolution. The very existence of the CMB underscores a profound truth about cosmological time. While we are entrenched in the present, the universe itself is a vast archive of its own history, written in the language of light and matter. Each photon we observe carries with it a story from the past, a whisper from a time when the universe was young and full of potential. As we continue to explore the cosmos, we find that the expansion of the universe is not a uniform process. Observations reveal that this expansion is accelerating, driven by a mysterious force dubbed dark energy. This enigmatic presence accounts for approximately 68% of the universe's total energy content, yet it remains one of the greatest mysteries in contemporary physics. Its discovery has profound implications for our understanding of time, suggesting that the universe's fate is one of endless expansion, with galaxies drifting ever farther apart into the cosmic night. The acceleration of the universe's expansion hints at a future where stars exhaust their fuel, galaxies grow dim, and the cosmos becomes a cold, dark expanse. This potential end state, often referred to as the heat death, paints a picture of a universe that becomes increasingly less hospitable to life, raising profound questions about the ultimate nature of time and existence. Yet even in this distant, speculative future, time remains the quiet architect of the universe's fate. It is the silent custodian of change, guiding the cosmos through its myriad transformations. From the violent birth of stars to their serene demise, time shapes the universe in ways both grand and subtle. As we stand on our small blue planet, gazing into the night sky, we find ourselves connected to this cosmic dance. Each star, each galaxy, is a reminder of time's vast tapestry, of the story writ large across the heavens. And though our lives are but fleeting moments in this grand narrative, we are nonetheless a part of it, participants in a universe where time's gentle hand guides all things towards the future. In contemplating cosmological time, we reflect not only on the universe's past, but also on our place within it. We find a sense of continuity, a thread woven through the ages that speaks to the enduring nature of time itself, a force that binds the cosmos in a shared journey through the epochs, from the fiery birth of the universe to the quiet realms of tomorrow. In the gentle whispers of the cosmos, there lies an idea so curious, so profound, that it nudges at the very edges of our understanding of time. It is the notion of the block universe, a concept that invites us to step back from our daily perception of time's relentless march, and instead consider a view where past, present, and future coexist in a grand, timeless tapestry. Imagine, if you will, a vast, intricate sculpture carved from the finest marble. Every detail, every contour is fixed, unchanging, and eternal. This sculpture does not evolve or alter with the passage of time, for it embodies all moments simultaneously. In this analogy, the block universe stands as a timeless picture of reality, where every event, every moment in space-time exists eternally, much like the unyielding marble of our sculpture. This perspective challenges our inherent belief in the flow of time, the ceaseless progression from one moment to the next that shapes our lives and experiences. We often perceive time as a river flowing inexorably onward, carrying us from the past into the future. But within the framework of the block universe, time resembles more a sprawling landscape, where all moments are laid out before us. We are not so much traveling through time as we are experiencing different parts of this unchanging expanse. The origin of this concept can be traced back to Albert Einstein's theory of relativity, which elegantly weaves together the fabric of space and time into a four-dimensional continuum known as space-time. Within this framework, time is treated as another dimension, akin to the spatial dimensions we navigate in our everyday lives. Just as every point in space is fixed and real, so too are all points in time. To grasp this idea, let us contemplate a simple analogy. Consider a loaf of bread, each slice representing a distinct moment. In the block universe, every slice exists simultaneously, from the heel of the loaf to its core, each moment as real and present as the others. Our perception of time's flow is akin to moving through these slices, experiencing them one by one, yet within the loaf they all coexist. This view of time raises intriguing questions about the nature of reality and our place within it. If all moments are equally real, what does it mean for our understanding of change and causality? How does this affect our sense of free will and the choices we make? In the block universe, the future is as fixed as the past, suggesting that our actions, though seemingly spontaneous, are already etched into the structure of space-time. Yet, this does not imply a predetermined existence devoid of meaning or agency. Rather, it invites us to reconsider how we perceive the flow of time and our role in the universe. The block universe suggests a reality where the narrative of our lives is already written, but within this narrative we still play our parts, experiencing the richness and complexity of each moment. The notion of the block universe also has profound implications for our understanding of memory and anticipation. If all moments are equally real, then memory is not a mere record of past events, but a perspective from which we view different parts of the space-time landscape. Anticipation, too, becomes a way of glimpsing future slices of this grand loaf, already present but yet to be experienced. As we delve deeper into the implications of the block universe, we are reminded of the intricate dance between physics and philosophy. The idea challenges us to rethink our most basic assumptions about time, urging us to explore the boundaries of knowledge and perception. It invites a gentle curiosity about the nature of reality and our place within it, encouraging us to embrace both the mystery and the beauty of a universe where time is not a fleeting river, but a timeless expanse. In contemplating the block universe, we find ourselves at the intersection of science and wonder, where questions abound and answers remain elusive. It is a reminder that, despite our advances in understanding the cosmos, there is still much to ponder and explore. And perhaps, in this pondering, we find a quiet solace, a gentle acceptance of the mystery that surrounds us as we continue our journey through the timeless landscape of existence. In a quiet corner of philosophical contemplation, there resides a view as intriguing as it is contentious: presentism. This perspective suggests that only the present moment holds true reality. The past has ceased to exist, and the future is yet to be. We dwell solely in the fleeting now. As we explore this notion, we find ourselves standing at the crossroads between intuition and the intricate tapestry of modern physics. To the untrained eye, presentism might appear self-evident. After all, our everyday experience is dominated by the immediacy of the present. The ticking of a clock, the rustle of leaves in the breeze, the ebb and flow of our breath. These all occur in a momentary now that feels undeniably real. Yet, as we probe deeper, we encounter a web of philosophical and scientific quandaries. At its core, presentism is a philosophical interpretation of time that diverges from other temporal philosophies, such as eternalism, which posits that past, present, and future are equally real. Presentism asserts that only the present exists, and it is constantly refreshed as moments pass. This might resonate with our intuition, but it raises significant challenges when we juxtapose it with the framework of modern physics. Physics, particularly in the realm of relativity, presents a universe where time is interwoven with space into a four-dimensional fabric known as space-time. In this framework, time does not progress in a linear fashion as we might perceive it. Instead, it is part of a continuous landscape where past, present, and future coexist. The implications of this are profound, suggesting that every moment, like a bead on a string, is fixed in place within the vast expanse of the universe's history. Einstein's theory of relativity further complicates the picture. According to relativity, the concept of simultaneity is not absolute. Two events perceived as simultaneous by one observer may not be so for another, moving at a different velocity. This relativistic effect challenges the idea of a universal present that ticks uniformly across the cosmos. In such a universe, the notion of a singular objective present becomes slippery, if not untenable. Yet, presentists are not without their counter-arguments. They might argue that the physics of relativity does not necessarily negate the reality of the present, but rather complicates our understanding of it. They suggest that our perception of time's flow is a fundamental aspect of human consciousness, one that physics alone may not fully capture. In this view, the present is a unique intersection where the potential of the future becomes the actuality of the past through the conduit of our awareness. Indeed, the brain's role in constructing our sense of time cannot be understated. Neurological studies reveal that our perception of time is a complex interplay of memory, sensory input, and cognitive processing. The brain does not merely record time like a passive observer. It actively constructs our temporal experience, presenting the past as memory and the future as anticipation, all anchored in the present moment. Yet, while presentism speaks to our human experience, it encounters difficulties when faced with the empirical rigor of scientific inquiry. For instance, if only the present is real, how do we account for the enduring nature of physical laws or the consistency of historical records? These questions invite further philosophical inquiry and scientific investigation. Some philosophers have sought to reconcile presentism with the findings of modern physics through alternative approaches, such as the notion of a moving spotlight. This metaphor suggests that the present is akin to a spotlight moving across the stage of time, illuminating moments as they come into and fade from existence. This view preserves the idea of a dynamic present while acknowledging the broader landscape of space-time. Such reconciliations demonstrate the rich interplay between philosophy and science, each offering unique insights into the nature of time. While presentism may not align neatly with the models of physics, it serves as a reminder of the profound mystery that time poses to both disciplines. It invites us to ponder the essence of our existence, to reflect on the way we perceive and engage with the world around us. In contemplating presentism, we are reminded that the philosophical exploration of time is as much about the questions it raises as the answers it provides. The notion of a singular, ever-changing present challenges us to consider the nature of reality itself, a pursuit that continues to inspire thinkers and dreamers alike. As we linger in the present moment, we are invited to embrace the mystery of time, acknowledging its complexity and our role within its flowing stream. Thus, while presentism may face formidable challenges from the perspective of modern physics, it endures as a poignant reminder of the immediacy of our lived experience. It reflects the human desire to anchor ourselves in a world that, at times, feels as transient as the moments we inhabit. As we journey through the unfolding narrative of time, we are left to wonder whether the present is a fleeting moment or the enduring heart of our existence. Imagine, if you will, a vast and open landscape, stretching out in all directions under a serene twilight sky. This is not a landscape of hills or valleys, but one composed of time itself. In this view, known as eternalism, time is not a river through which we drift, buffeted by the currents of the present and past. Instead, time is a landscape through which we might wander, if only we could perceive it fully. Eternalism suggests that every moment past, present, and future exists together in a grand, timeless tapestry. Picture each moment as a page in a boundless book, each page equally real, its events unaltered by the turning of pages. In this realm, the sensation of time flowing, of one moment slipping into the next, is an illusion crafted by our minds. We are not so much travelers on a journey, but observers of a panorama where every tableau is already painted and placed. This notion, while intoxicatingly poetic, is grounded in serious scientific and philosophical contemplation. It aligns comfortably with Einstein's theory of relativity, which reveals that time is intertwined with space, forming a single entity, space-time. In this framework, the past and future are as concrete as the street you walk upon or the sky above. Relativity shows us that different observers, moving relative to one another, might disagree on the chronological order of events, yet each perspective holds its truth. Such a perspective reshapes our understanding of memory and identity. If every moment is equally real, our memories are not mere shadows of what once was, but windows into sections of the landscape we have traversed. They are reflections of our path, not mere echoes. Our identity, then, becomes a collection of these snapshots, a mosaic of experiences that do not fade with the passage of time, but remain fixed in the eternal landscape. Consider, too, the implications for free will and determinism. If each moment is eternally fixed, like stars in a constellation, does this mean all is predetermined? Or do we still carve our paths through this timeless terrain? These are questions that stir deep philosophical inquiries, challenging us to ponder the nature of choice and agency when time is viewed as a static entity. In the realm of physics, Eternalism provides a compelling explanation for the absence of a universal now. Unlike our everyday experience, where now feels like a sharp line dividing past from future, physics offers no such demarcation. In the eternal landscape, the present is but one vantage point among countless others, all equally accessible to the eye of the universe. This view also influences our interpretation of relativity. In Einstein's universe, time dilation and the relativity of simultaneity suggest that time's progression is not a simple linear affair. Instead, it is flexible, influenced by motion and gravity, intertwining with space to create a fabric that defies our everyday intuitions. Eternalism elegantly accommodates these phenomena, suggesting that all moments are woven into the fabric of space-time, their order and flow a matter of perspective. Yet, eternalism challenges us on a profound level. It asks us to reconsider the flow of time, the comforting notion that the future is a blank slate, ready to be filled with possibilities. Instead, it posits a universe where every moment is already etched into the fabric of reality. This can feel unsettling, a departure from the comforting narrative of time as a river carving new paths through the land. Nevertheless, this timeless perspective offers a certain kind of solace. If all moments exist simultaneously, then nothing is truly lost to time. The past remains as real as the present, the future as tangible as the past. This idea, while abstract, can lend a sense of permanence and continuity to our existence, providing comfort in the constancy of the cosmos. Eternalism, then, is not merely a scientific concept, but a lens through which we might view our lives. It invites us to appreciate each moment for its place in the greater tapestry, to see our experiences as part of a grand, eternal narrative. It asks us to embrace the notion that our lives, in all their complexity and beauty, are woven into the fabric of the universe, a lasting part of the cosmic story. In contemplating this view, we are reminded of the delicate interplay between science and philosophy, where ideas about time and existence dance together in an intricate waltz. Eternalism challenges us to think deeply about our place in the universe, to consider the nature of reality beyond the boundaries of our immediate perception. As we stand upon this timeless landscape, we are invited to reflect on the nature of our journey, to ponder the paths we tread and the vistas we glimpse. In the stillness of this eternal view, we find a quiet space for contemplation, a moment of connection with the infinite and the enduring. Here, in the realm of eternalism, we are encouraged to see time not as a fleeting river, but as a serene and eternal landscape, ever present and ever true. When we ponder the notion of time, it often appears to us as an unbroken stream, a gentle river flowing ever onward, carrying us from the cradle to the grave. Yet, within the halls of scientific inquiry and philosophical reflection, the nature of this flow is anything but straightforward. The debate over whether time truly flows, and if so, how, continues to stir the minds of those who seek to understand the fabric of reality. Let us begin with the dichotomy between psychological time and physical time. Psychological time is the realm of subjective experience, where moments can stretch languidly or pass in a blink, dictated by our mental state rather than the steady tick of a clock. Physical time, on the other hand, is the objective measure, the domain of seconds and minutes, unyielding and indifferent to human perception. Our brains are remarkable organs, adept at crafting a tapestry of continuity from the myriad stimuli that bombard our senses. This sense of temporal flow, the seamless transition from past to present to future, is a construct, an illusion born of neural processes. It is a testament to the brain's ability to integrate information, to weave memories and anticipations into a coherent narrative that we call life. In understanding how the brain conjures this sense of time's passage, we must delve into the workings of memory and anticipation. Memory serves as the anchor, providing a reference point from which we gauge the passage of time. It is a delicate repository of past experiences, prone to distortion and decay, yet vital in constructing our temporal framework. Anticipation, meanwhile, propels us forward, allowing us to project ourselves into potential futures, to plan and to hope. The brain's internal clock systems, intricate networks of neurons and biochemical signals, play a crucial role in this temporal orchestration. The suprachiasmatic nucleus, nestled within the hypothalamus, acts as the master clock, synchronizing the body's rhythms with the cycles of day and night. It governs the circadian rhythms that regulate sleep, feeding, and hormone production, ensuring that our biological cycles align with the external world. Yet, these internal clocks are malleable, influenced by factors both internal and external. Stress, fatigue, and illness can warp our perception of time, making minutes seem like hours or vice versa. Similarly, engaging activities or deep concentration can lead to a phenomenon known as time flies, where our awareness of time's passage diminishes. The sense of continuity, of a flowing time, is also shaped by the brain's tendency to create narratives. Humans are storytellers by nature, and our perception of time is often framed as a story with a beginning, middle, and end. This narrative construction is not merely a byproduct of language, but a fundamental aspect of cognition, allowing us to make sense of the world and our place within it. Consider the experience of déjà vu, that eerie sensation of having lived through the present moment before. It is a reminder of the brain's propensity for pattern recognition, for linking past experiences with current stimuli in ways that sometimes lead to temporal dissonance. Such phenomena underscore the complexity of time perception and the brain's role in sculpting our temporal experience. The debate over the flow of time also touches upon philosophical questions, challenging the assumption that time is a relentless, unidirectional stream. Some philosophers argue that time, like space, is a dimension in which all moments coexist, and the sensation of flow is an artifact of human consciousness. Others maintain that the passage of time is a fundamental aspect of reality, an irreversible process that defines change. Einstein's theories of relativity introduced the notion that time is flexible, intertwined with the fabric of space, and subject to the influence of gravity and motion. This scientific perspective complicates the idea of a universal temporal flow, suggesting instead a mosaic of localized time experiences, each contingent on one's relative position and velocity. Despite these scientific insights, the human experience of time remains deeply personal and visceral. We measure our lives in years and seasons, in birthdays and anniversaries, marking the passage of time with rituals and milestones. Our sense of temporal flow is an essential aspect of identity, providing continuity to our existence and meaning to our actions. In the end, the question of whether time truly flows may be less about objective truth and more about the stories we tell ourselves. It is a dance between the measurable and the immeasurable, the seen and the unseen, the clockwork of the universe and the poetry of the human soul. As we continue to explore the mysteries of time, we may find that the answers lie not in the stars or equations, but in the quiet reflections of our wandering minds. In the quiet pursuit of understanding time, we inevitably stumble upon one of its most enigmatic and alluring possibilities: time travel. The very notion conjures images of science fiction, adventurous escapades across centuries, and the chance to witness the unfolding of history's grandest events. Yet, behind the imaginative tales resides a serious scientific inquiry, one that compels us to ask, what does physics truly allow? At the heart of time travel discussions in physics lies the concept of closed, time-like curves, CTCs. These are peculiar solutions to Einstein's equations of general relativity, which suggest that, under certain conditions, the fabric of space-time could be bent back upon itself, forming a loop. In such a loop, an object could, in theory, travel along a path that returns to its own past, creating a journey through time. One of the most famous theoretical constructs in this domain is the idea of a wormhole. These hypothetical bridges in space-time, first proposed by Albert Einstein and Nathan Rosen, are often depicted as shortcuts connecting distant points in the universe. If traversable, a wormhole might allow an intrepid traveler to step into a distant part of the cosmos or even into another era. The allure of wormholes lies in their potential to bypass the vast expanses of space and time, offering a tantalizing glimpse into the possibilities of the universe. However, the practicalities of such a journey are beset by formidable challenges. For a wormhole to remain stable and open long enough for passage, exotic matter with negative energy density is required. This type of matter, unlike anything we currently understand, would be necessary to counteract the natural tendency of the wormhole's throat to collapse under gravitational forces. While the existence of exotic matter is speculative, the mathematical framework that supports the concept of wormholes remains a fascinating area of study. The possibility of time travel through closed, time-like curves or wormholes inevitably leads us to consider the paradoxes that arise. One of the most well-known is the grandfather paradox, which poses a curious dilemma. What happens if a time traveler were to journey back and prevent the birth of their own ancestor? Such an action would seemingly erase the traveler's very existence, thus preventing the journey in the first place. This paradox highlights the intricate relationship between cause and effect, challenging our understanding of temporal sequences. To reconcile these paradoxes, physicists have explored various theoretical solutions. One such proposal is the Novikov self-consistency principle, named after the Russian physicist Igor Novikov. According to this principle, any actions taken by a time traveler in the past must be consistent with the traveler's history, as already known. In essence, the universe conspires to prevent paradoxes, ensuring that the traveler's interventions cannot alter the course of events in a manner that contradicts their own timeline. Another intriguing concept is that of multiple timelines or parallel universes. This idea suggests that each action taken by a time traveler might spawn a new branching timeline, allowing for different versions of history to coexist. In this view, traveling back in time and altering an event would not erase the original timeline, but would instead create a divergent path. While this multiverse theory offers a potential resolution to paradoxes, it remains a speculative and largely untestable hypothesis. The allure of time travel continues to captivate our imagination, driving both scientific inquiry and philosophical reflection. It invites us to ponder the nature of time itself, urging us to question whether past and future are fixed or malleable. As we delve deeper into the quantum realm, where the rules of classical physics begin to blur, new possibilities emerge. Quantum mechanics, with its inherent uncertainties and peculiarities, might offer fresh insights into the nature of time and the feasibility of traversing its currents. Despite the theoretical groundwork laid by Einstein and others, the practical realization of time travel remains elusive. The energy requirements, technological challenges, and potential for paradoxes present formidable obstacles. Yet, the pursuit of understanding time travel is not merely about the quest to build a time machine. It is about probing the very boundaries of our knowledge, seeking to unravel the mysteries of a universe that is as vast as it is complex. As we continue to explore the intricate dance of space-time, we are reminded that the journey itself is as important as the destination. The exploration of time travel serves as a testament to human curiosity, a reflection of our desire to comprehend the cosmos in all its grandeur. In the quiet moments of contemplation, we find ourselves pondering not just the possibility of moving through time, but the deeper implications of such a journey on our understanding of reality and our place within it. In this pursuit, we are guided not only by the equations of physics, but by the enduring human spirit that seeks to transcend the boundaries of the known. Time travel, whether ultimately realized or not, remains a powerful symbol of our collective imagination, a reminder that the universe is full of wonders yet to be discovered. And so we continue our quiet journey through time, ever mindful of the mysteries that lie ahead. In our quiet exploration of time travel, we arrive now at the boundaries set by nature itself. While the concept of traversing through time captivates the human imagination, the universe, in its quiet wisdom, imposes constraints that confine our temporal wanderings. Let us gently delve into these limits, pondering the subtle interplay of physics and the natural order. Time travel, with its tantalizing promise of visiting the past or glimpsing the future, finds itself enshrined in the annals of science fiction. Yet, when scrutinized through the lens of physics, it encounters formidable obstacles. One key theoretical construct that acts as a guardian of the temporal order is the chronology protection conjecture. Proposed by the esteemed physicist Stephen Hawking, this conjecture suggests that the laws of physics inherently discourage time travel on a macroscopic scale, thus preserving the chronological sequence of events. At the heart of this conjecture lies the notion of closed time-like curves, paths through space-time that loop back upon themselves, theoretically allowing an object to return to its own past. These curves emerge naturally in certain solutions to Einstein's equations of general relativity, particularly those involving rotating black holes or hypothetical structures known as wormholes. However, The existence of such curves raises profound questions about causality and the potential for paradoxes, such as the well-known grandfather paradox, where a time traveler might prevent their own existence. The chronology protection conjecture posits that quantum effects, which are generally negligible at everyday scales, would become significant near these closed, time-like curves, generating instabilities that prevent their formation. This idea is akin to a cosmic sensor, quietly ensuring that the fabric of space-time remains free from contradictions. In this way, quantum mechanics, with its inherent uncertainty and probabilistic nature, acts as a stabilizing force, preserving the linear flow of time as we perceive it. Beyond the chronology protection conjecture, we encounter the delicate concept of quantum instability. When we consider the quantum realm, where particles behave in ways that defy classical intuition, the possibility of time travel becomes even more elusive. Quantum fluctuations, those minute and ephemeral shifts in energy that occur spontaneously, could destabilize any structure attempting to facilitate time travel. The very act of traversing time may require conditions so precise that the slightest perturbation could render the endeavor futile. In addition, the energy requirements for creating and sustaining a passage through time remain daunting. Theoretical constructs, such as traversable wormholes, demand negative energy, a concept that challenges our understanding of matter and energy. While quantum mechanics allows for the temporary existence of negative energy in the form of virtual particles, harnessing such phenomena on a scale necessary for time travel presents an insurmountable challenge with our current technological and theoretical capabilities. Moreover, even if one were to circumvent these hurdles, the fundamental nature of time itself remains a barrier. Time, as we experience it, flows inexorably in one direction, from past to future. This unidirectional flow is intimately tied to the second law of thermodynamics, which dictates that entropy, or disorder, tends to increase over time. This gives rise to the arrow of time, a concept deeply rooted in the fabric of our universe, subtly reinforcing the notion that the past is irretrievable and the future is yet to unfold. As we contemplate these barriers, it becomes apparent that the elegance and complexity of the universe are reflected in its restraint. The laws of physics, with their intricate balance and quiet authority, seem to suggest that time travel, while a fascinating construct, may remain forever beyond our grasp. Yet, this should not dishearten us. Instead, it invites us to appreciate the present moment, the here and now, as a unique and fleeting experience in the grand tapestry of time. In this reflective pause, we find solace in the notion that the journey through time is not merely about reaching destinations long past or yet to come. Rather, it is about understanding our place within the continuum, recognizing the beauty of each moment as it gently unfolds. Time, with all its mysteries and constraints, remains a profound and enduring frontier, inviting us to explore its depths with curiosity and wonder. And as we continue our quiet journey, we are reminded that the limits of time travel, far from being a hindrance, are a testament to the universe's harmonious design, guiding us toward a deeper appreciation of the fleeting gift of now. In the quiet chambers of the mind, time weaves itself into the fabric of our consciousness, a thread that seems both tangible and ethereal. As we journey through the tapestry of life, Our perception of time is shaped not just by the ticking of clocks, but by the ebb and flow of our thoughts, memories, and anticipations. It is this intricate dance of mental processes that grants us the profound sensation of time passing. Memory, that keeper of our past, plays a pivotal role. Our ability to recall experiences not only provides a sense of continuity, but also a framework through which we measure the passage of time. When we reminisce about a summer long gone or a fleeting moment of joy, we are engaging in a mental reconstruction, a narrative that gives temporal order to the myriad events of our lives. Each memory is like a bead on the thread of time, and the act of recalling it, a gentle tug that reaffirms its position in our personal history. Anticipation, akin to memory's forward-looking counterpart, draws us into the realm of the future. Our brains are wired to predict and plan, constantly sketching scenarios that have yet to unfold. This ability to envisage what lies ahead imbues our present with a sense of direction and purpose. In this way, anticipation serves as a bridge between the now and the not. Yet, a reminder that time is not simply a sequence of static moments, but a dynamic continuum. At the heart of these cognitive processes lies the narrative self, the storyteller within each of us. It is this inner narrator that knits the fragments of memory and anticipation into a coherent story, a personal saga that is uniquely ours. Through this narrative, we find meaning in the passage of time, understanding our place within the larger mosaic of existence. It is this ongoing tale that provides the sensation of flow, the feeling that time is moving forward, carrying us along its current. The brain, ever the masterful architect, orchestrates these elements through a complex network of neural mechanisms. Studies in neuroscience have shown that different regions of the brain are involved in encoding memories, projecting future events, and maintaining a sense of self. The hippocampus, for instance, plays a crucial role in forming new memories, while the prefrontal cortex is heavily engaged in planning and decision-making. These regions, along with others, work in concert to create the seamless experience of time that we often take for granted. Yet, our perception of time is not always consistent. It is subject to the whims of circumstance and state of mind. An hour spent in joyous company may feel like mere minutes, while a few minutes in discomfort can stretch into eternity. This elasticity of subjective time highlights the influence of our emotional and psychological states on our temporal experience. It is as if time bends and warps in response to our inner world, a reminder that while the clock may tick steadily on, our perception of its passage is anything but linear. Moreover, the passage of time is deeply intertwined with our sense of identity. As we age, our memories accumulate and our anticipations evolve, shaping the narrative of who we are. This continuous interplay between past experiences and future aspirations forms the foundation of our personal identity, a temporal tapestry that defines us. It is through this lens of self that we interpret the events of our lives, assigning them significance and weaving them into the ongoing story of our existence. In exploring why we feel time passing, we encounter not just the mechanics of memory and anticipation, but the very essence of what it means to be conscious. Time, in this context, is more than a backdrop for our lives. It is an integral part of our conscious experience, a dynamic force that shapes our understanding of the world and our place within it. This awareness of temporal flow is a hallmark of human cognition, a testament to the complexity and subtlety of the mind. As we reflect on the relationship between time and consciousness, we are drawn into a deeper appreciation of the mysterious interplay between the mind and the cosmos. Time is both a measure and a metaphor, a canvas upon which the story of our lives is painted. In this gentle exploration, we find not only the science behind our perception, but also a quiet contemplation of the human condition. Through the lens of time, we see ourselves more clearly, understanding that we are both creators and subjects of our temporal experience. Thus, the passage of time is felt not just through the ticking of the clock, but through the rhythms of our minds and hearts. It is this intimate connection between time and consciousness that enriches our lives, offering a profound sense of continuity and presence. And so, in the silent whispers of the mind, we continue to journey through time, ever aware of its passage, ever engaged in the dance of memory, anticipation, and the narrative self. Let us embark on a contemplative journey through the varied ways in which time is experienced by the myriad forms of life on our planet. In contemplating these diverse experiences, we gain a deeper appreciation for the multifaceted nature of time itself as it unfolds across different scales of existence. Consider the humble mayfly, whose entire adult life is encapsulated within the span of a single day. To us, it might seem an ephemeral existence, but for the mayfly, that day is an entire lifetime, filled with experiences and the fulfillment of its biological purpose. In contrast, the ancient bristlecone pine, standing steadfast on a lonely mountainside, witnesses the passage of centuries. Its life stretches across millennia, a slow and steady rhythm that contrasts sharply with the frantic dance of the mayfly. The metabolic rates of organisms often dictate their perception of time. Creatures with rapid metabolisms, such as hummingbirds, experience life in a flurry of swift movements and rapid heartbeats. For them, the world might appear to unfold in slow motion, each second brimming with activity and vibrancy. Their wings beat at a dizzying pace, a blur to our eyes, yet to them, it is a natural cadence, perfectly in tune with their internal clock. In contrast, the giant tortoise, with its languid movements and slow metabolism, inhabits a world where time seems to stretch and elongate. Days pass with a gentle ease, and the tortoise ambles through life with a patience that belies the urgency we often associate with the passage of time. Its heart beats slowly, each pulse a reminder of the deep time within which it exists. In the tortoise's world, there is no rush, only the steady march of moments, each savored in its own time. These differences in temporal perception are not merely a matter of speed or slowness. They reflect the fundamental nature of life itself. Each organism is attuned to its environment, its timescale, a reflection of the ecological niche it occupies. For the cheetah, whose bursts of speed are a testament to its evolutionary prowess, time is a series of fleeting opportunities, each chase a matter of survival. In those brief, explosive moments, time for the cheetah is distilled into an essence of urgency and precision. The trees of a dense forest, by contrast, are bound to a different rhythm. Their lives are chronicled in the rings of their trunks, each layer a testament to the passing years. They stand as silent witnesses to the epochs, their time marked not by the ticking of a clock, but by the slow procession of seasons. For them, time is measured in the cycles of growth and dormancy, the ebb and flow of nutrients and sunlight. These contrasting experiences of time invite us to ponder the subjective nature of temporal perception. While humans measure time in seconds, minutes, and hours, other creatures perceive it through the lens of their own existence. The swift, darting movements of a dragonfly are no less valid an experience of time than the unhurried, deliberate steps of an elephant. Indeed, the physiology of perception plays a significant role in this diversity. The neural processes that underpin our awareness of time are finely tuned to our own biological rhythms. For a small mammal with a high metabolic rate, neural signals travel rapidly, and the world is experienced in a rapid succession of events. In contrast, larger animals with slower metabolism experience these signals at a more leisurely pace, resulting in a different temporal awareness. The concept of time, then, is not a monolithic entity, but a tapestry woven from the varied threads of life. Each organism, from the tiniest insect to the mightiest tree, experiences time through the lens of its own existence, shaped by evolution to suit its needs and environment. This rich diversity of temporal experience speaks to the adaptability and ingenuity of life itself. Moreover, as we consider these different ways of experiencing time, we are reminded of the interconnectedness of all life forms. The swift movements of a predator and the slow, deliberate growth of a plant are part of the same ecological web, each playing a role in the complex dance of life. Time, in its many forms, is the thread that binds this tapestry together, a quiet framework that supports the myriad stories unfolding across the natural world. In contemplating these varied experiences of time, we find a gentle reminder of the richness of life and the beauty of diversity. Each organism, with its unique perception of time, adds to the symphony of existence, a testament to the wonder and complexity of the natural world. As we reflect on these different timescales, we are invited to step outside our own temporal boundaries and appreciate the myriad ways in which time is woven into the very fabric of life. In the gentle, rhythmic dance of the universe, time stands as both a measure and a mystery. As our understanding of time has evolved, so too have the tools we use to measure it. From the shadows cast by ancient sundials to the precision of atomic clocks, humanity's quest has always been to capture the essence of time with increasing accuracy. And now, on the horizon of this quest, we find ourselves on the brink of yet another revolution in timekeeping, the optical lattice clock. The optical lattice clock is a marvel of modern science, a testament to our relentless pursuit of precision. Unlike its predecessors, this clock relies on the oscillations of atoms, which, when trapped in a lattice of laser light, can be measured with extraordinary accuracy. These oscillations occur at frequencies far higher than those used in traditional atomic clocks, allowing for a much finer division of the second. This is a leap forward, promising a level of precision that was once beyond our reach. As we explore the implications of this technological advancement, we find ourselves contemplating the possibilities it opens up. The potential of optical lattice clocks extends far beyond merely keeping time. With their unparalleled accuracy, they could redefine the second itself, setting a new standard for time measurement. This redefinition could, in turn, refine our understanding of the universe. Consider the impact on technology, for instance. Our modern world relies on precise timekeeping in ways that are both visible and unseen. Global Positioning Systems, or GPS, are one such example. These systems depend on the synchronization of clocks on satellites orbiting Earth. Even a tiny discrepancy can lead to significant errors in positioning. With the advent of optical lattice clocks, the accuracy of GPS could be enhanced, leading to improvements in everything from navigation to the timing of financial transactions. Moreover, these clocks could play a crucial role in scientific research. In the realm of physics, where measurements of time and frequency are paramount, greater precision can lead to new insights. For instance, optical lattice clocks could be used to test the fundamental laws of physics, such as Einstein's theory of general relativity, with unparalleled accuracy. By comparing the ticking of clocks at different altitudes, scientists can measure the effects of gravity on time with greater precision, offering deeper insights into the nature of space-time. Beyond physics, the impact of improved timekeeping extends to the study of the Earth itself. Geoscientists could use optical lattice clocks to monitor minute changes in the Earth's gravitational field, providing valuable data on tectonic activity and sea level changes. Such information could enhance our understanding of the Earth's dynamic processes and improve our ability to predict natural phenomena. The journey of timekeeping technology is a testament to humanity's curiosity and ingenuity. Each advancement brings with it new possibilities and challenges, inviting us to explore the boundaries of knowledge. Optical lattice clocks, with their promise of unprecedented precision, represent a significant step forward in this journey. They remind us that, while time itself may be a constant backdrop to our lives, our understanding of it is ever evolving. As we contemplate the future of time, we find ourselves reflecting on the broader implications of these advancements. What does it mean to measure time with such precision? How does it shape our perception of the world? In many ways, the pursuit of accurate timekeeping mirrors our quest for understanding, a journey that is as much about the questions we ask as the answers we find. In this serene exploration of time, we are reminded of the delicate interplay between science and philosophy. Time, in its essence, is both a scientific concept and a philosophical enigma. It is the thread that weaves the fabric of our existence, connecting past, present, and future in a continuous tapestry. As we advance our ability to measure time, we deepen our appreciation for its complexity and its beauty. In the gentle passage of moments, we find the quiet rhythm of time itself, a rhythm that, like the ticking of a clock, is both familiar and profoundly mysterious. As we stand on the cusp of a new era in timekeeping, we are in the quiet expanse of the universe, where galaxies drift like luminescent islands across the cosmic ocean, a curious notion has begun to take root in the minds of physicists and philosophers alike. This notion proposes that time, that ever-familiar flow which we navigate daily, might not be as fundamental as we once thought. It suggests that time could be an emergent phenomenon, a gentle ripple on the surface of a deeper, timeless reality. To explore this idea, we must first venture into the realm of quantum gravity, where the laws of quantum mechanics and general relativity seek a harmonious coexistence. At this juncture, the universe reveals its intricate complexity, akin to an artist's canvas where the brushstrokes of time and space blend seamlessly. Here, theories like loop quantum gravity and the holographic principle offer glimpses into a universe that may not rely on time as a foundational element. Loop quantum gravity, for instance, reimagines the very fabric of space-time. Rather than viewing it as a smooth continuum, this theory envisions it as a lattice of discrete loops, each one a minuscule bundle of geometry. In this framework, time might not flow continuously, but rather emerge from the quantum interactions of these loops. It is as if the universe were a vast symphony, with time as the melody arising from the complex interplay of notes. Not an independent entity, but an emergent harmony. The holographic principle, meanwhile, presents a different conceptual tapestry. It posits that our three-dimensional universe might be a projection from a two-dimensional surface, much like a hologram. If this is true, then time, as we experience it, could be an illusion born of our perception, a mere shadow of deeper dynamics occurring beyond our observable dimensions. In this view, time's passage might be akin to flipping through pages of a book, each page a collection of events fixed in a timeless narrative. While these theories are profoundly speculative, they invite us to ponder the implications of a universe without a fundamental time. If time is emergent, what does this mean for our understanding of cause and effect, of past, present, and future? Could the very foundations of our reality be more fluid than previously imagined, with time but one of many emergent properties of a grander cosmos? Consider for a moment the implications for our perception of history and future. If time is not fundamental, does history become merely a story we tell ourselves, a sequence crafted by human consciousness to make sense of our experiences? And what of the future? Does it remain an unwritten chapter waiting to unfold, or is it a tapestry already woven, hidden from view until the moment we arrive? While such musings may seem abstract, they touch upon the essence of what it means to be human. Our lives are woven into the fabric of time, each moment a thread in the tapestry of existence. Yet, if time is not the foundational thread but an emergent pattern, we are called to reconsider our place in the universe, to embrace the possibility that our understanding of time may be as much a reflection of our minds as it is of the cosmos. In this timeless perspective, we find echoes of ancient philosophies that have long pondered the nature of reality. The idea that time might be an illusion resonates with the teachings of Eastern traditions, where the eternal present is often emphasized over linear progression. Here, science and philosophy converge, each offering insights into the profound mystery of existence. As we journey through these speculative realms, it is crucial to remember that the quest to understand time is as much about exploration as it is about answers. The universe, in its vastness, continues to be a source of wonder, inviting us to embrace both the known and the unknown. Whether time is fundamental or emergent, its study enriches our understanding of the cosmos, offering glimpses into the profound interconnectedness of all things. As we reflect on the possibility that the universe might have a timeless foundation, we are reminded of the beauty inherent in the search itself. It is a journey that transcends the boundaries of science and philosophy, inviting us to contemplate the nature of reality. As we draw our exploration of time to a gentle close, let us pause for a moment to reflect on the quiet profundity of our journey. Time, that ever-present yet elusive companion, has guided our thoughts through a tapestry woven from the threads of physics and philosophy. It is a framework that both defines and transcends the boundaries of existence, a silent architect of reality itself. In contemplating time, we find ourselves straddling the realms of the tangible and the abstract. It is a construct that measures the rhythm of the universe, marking the passage of days and the unfolding of history. Yet, it is also a profound mystery that invites deeper reflection. Time's dual nature, as both a scientific measure and a philosophical enigma, enriches our understanding of the cosmos and our place within it. Throughout this discourse, we've encountered time as a dimension, a continuum, and an arrow. We've observed its malleability through the lens of relativity, where it bends and stretches in the presence of gravity and velocity. We've seen it as a relentless march towards entropy, an irreversible flow that shapes the universe's destiny. Yet, we've also entertained the notion of a block universe, where past, present, and future coexist in a timeless tapestry. The philosophical dialogues surrounding time provide a canvas for pondering existence itself. Is the present moment all that truly exists, or do other times hold equal reality? Such questions challenge our perceptions and provoke us to consider the nature of reality beyond the confines of our immediate experience. In merging the rigor of science with the depth of philosophy, we find ourselves contemplating time as a quiet framework of existence. It is a medium through which the universe expresses its myriad forms, a stage upon which the drama of life unfolds. Time connects the smallest particles and the grandest galaxies, orchestrating a cosmic symphony that resonates through the ages. As we reflect on this intricate dance, we find that time is also an intimate part of our personal narratives. It shapes our memories, our aspirations, and our sense of identity. Each moment, fleeting yet precious, contributes to the mosaic of our lives. Time's passage is marked by the rhythm of our heartbeats, the cycles of nature, and the transitions of day into night. In our pursuit of understanding, we find that time is both a lens and a mirror. It allows us to glimpse the origins of the universe, the evolution of life, and the future that awaits. Yet, it also reflects our own transience, reminding us of the impermanence of all things. Time invites us to ponder not only the vastness of the cosmos, but also the intricacies of the human experience. As we journey through the corridors of time, let us embrace the curiosity and wonder that it inspires. Let us cherish the moments of stillness and reflection, for they are the spaces where insight and wisdom reside. In these quiet intervals, we may find the answers to questions unasked and the solace of understanding. The exploration of time has led us to a point where science and philosophy converge, offering perspectives that enrich our appreciation of the universe. It is a gentle reminder that time is not merely a sequence of events, but a profound dimension that shapes the very fabric of reality. In closing, let us hold time with reverence, acknowledging its role as the quiet architect of existence. For in understanding time, we come to understand ourselves, our place in the universe, our connection to the past and future, and the fleeting yet eternal nature of the present moment. Time is a companion on our journey, guiding us with its silent, unyielding presence. As we navigate the labyrinth of existence, may we do so with mindfulness and gratitude, for in time we find the essence of life itself.